We have learned how to express an algebraic fractions with linear factors into two partial fractions. In this activity, we are going to learn how to express the algebraic fractions when the denominator given are repeated factors. Okay, what are repeated factors? For example, if you have a factor x plus 3, repeated means you have another one that is also x plus 3. Okay, and if you combine them, you will get bracket x plus 3 close bracket square. This is what you mean by repeated. The linear factor, you have two of the same kind. Let's give you another example. If you have a linear factor that says 2x plus 3, repeated means you have another one that is exactly the same, right? And if you were to combine them, it means it's bracket 2x plus 3 close bracket to the power of 2. Okay, so this one here means this is repeated. This is a repeated linear factor. Okay, so likewise for this, okay, this is also considered as a repeated linear factor. All right, so your this x minus 3 to the power of 2 can be written as bracket x minus 3 bracket x minus 3. All right, so if you were to compare this one they've underlined with your first linear factor, then of course the common denominator will be just this guy here, bracket x minus 3 close bracket times another x minus 3. All right, if you still don't understand, let me give you an example using numbers. You have learned how to simplify things like 2, 1 over 2, right? Let's say plus 3 over 4. But what is 4? 4 can be written as 2 squared, right? So what would be your common denominator be? The common denominator will be 2 squared, isn't it? Because 2 squared is 4. Right. So the first one, the 2, you multiply with a 2. And then the 2 squared, you multiply with 1. At the denominator, numerator, you times 1. So the answer you get is 5 over 4. Okay, this is what you've done when you're much probably in primary school. So the concept is still the same. Right. So you simplify it, you combine both of them, you will get this single algebraic fraction. So supposing we reverse the situation, you are given this algebraic fractions. How are you going to express it into two partial fractions? Right. So you will have, that means you look at the left now and you have to study this. Okay, the first fractions, can you see it's a constant over the linear factor? And then the second one is also a constant but over the repeated linear factor. Right, so this is exactly the rules that we're going to use here, this one. Okay, when you are given an algebraic fraction where the denominator is a repeated linear factor, right, then you can express it as two partial fractions. One of them is a over x minus 3, the other one is b over bracket x minus 3 close bracket squared, where a and b are both constant. All right, then you combine them as a single fraction as per normal. And it will lead you to this identity here. Right, and I let x equals to 3 because I want to eliminate a so that I can find the values of b. After I found the values of b, I can let x to be any other values but not 3. I can let it be 0, 1, 2 or anything but not 3 so that I can find the values of a. Right, so after that, I can just substitute the values of a and b into star star to get your two partial fractions here. So let's practice what we have learned. Let's recap what we have learned. So if you have a proper fractions when your denominator is a repeated linear factor, right, then you can actually express it into two partial fractions, a over ax plus b over bracket ax plus b to the power of 2. So first thing first, if you look at example 2, we have to check if what you're given is a proper fraction. So how do you know if it's a proper fraction? Let's look at the degree of your numerator, which is 2. Then the degree of your denominator would be 3. Are you able to explain why is it the degree of your denominator is 3? It is 3 because when you take x times x squared, you get x to the power of 3. So 3 means the highest power, hence the degree is 3. Right, so this is a proper fraction because the degree of the numerator is less than the degree of the denominator. Alright, so here comes the tricky part. Before you plunge into applying the rule, we should always manipulate, always look at the denominator and see if we can manipulate it to the complete form. What do I mean by saying that? Right, so if you examine the denominators that you are given, alright, this one can be factorized further. This one will have to remind you of your a squared minus b squared, which can be factorized into a minus b bracket a plus b. So hence your denominator will end up to be 3 linear factors where your x minus 2 is repeated. So I can combine them into a repeated form. Okay, right. So we learned that if your denominator is a repeated linear factor, we can break it up into two partial fractions, right? One of them is a over x minus 2, and the other one is b over x minus 2 squared. Then how about this third linear factor? We also learned in activity, I think the earlier activity, that if you have a proper fractions with linear denominator, then you can express it as what? A constant. We're going to let it be c over your linear factor. So in this example 2, in this particular questions, we can actually have 3 partial fractions. All right, so let's put all this into a proper form. So we're going to let all right, so we're going to combine them into a single fractions. So we need to have a huge line, and we need to decide what to use as the common denominator. Okay, so one of them has to be x plus 2, that's for sure. And between x minus 2 and x minus 2 squared, we have to take the biggest one. So the bigger one will be bracket x minus 2 close bracket squared. So that will be our common denominator. Right, so let's look at the first partial fraction. Okay, so from our first partial fractions, Right, we have 1x minus 2. So if you were to close up your power 2, right, then what you need to multiply a would be x plus 2 and bracket x minus 2. Then if you look at the second partial fractions, all right, at the denominator, you have already got this bracket x minus 2 close bracket squared. So we close it up. So your b would have to be multiplied with x plus 2. Let's look at the last one. Okay, so the last one, you have x plus 2. So we close it up. Then you will have to multiply it with x minus 2 close bracket squared. Okay, so this is how we go about finding all our numerators. Okay, and then these numerators that we have found will be equals to the numerator on your left hand side, which is 3x squared minus x plus 2. Okay, so we're going to use substitution method to find the constants a, b, c. So the first one, I'm going to let x equals to 2, because when I let x equals to 2, I can eliminate constant c. I can also eliminate constant a. All right, so this guy will be gone. So I will have b. 2 plus 2 is 4. This guy will be gone. My right hand side will be so I would have 4b equals to 12. B equals to 3. Okay, so I managed to find constant b. Right, then the next step is, okay, I'm going to let x equals to negative 2. Because if I let x equals to negative 2, I can eliminate a. I can also eliminate b. So that I can find the values of c. So therefore c would be 3 bracket negative 2 close bracket squared minus bracket negative 2 close bracket plus 2 divide by bracket negative 2 minus 2 squared. So c will be equals to 1. So I found the values of b and c. The last step, I can just use any values of x to find the last constant c. So I'm going to erase this part here. Okay, so I'm going to let x equals to 0. Right, so a over a bracket 0 plus 2 is 2, negative 2. I've already found the values of b, so I can just plug it in. 2, values of c is 1. This will be my left hand side. My right hand side will be, okay, so I will end up getting negative 4a plus 6 plus 4 equals to 2. Negative 4a will be negative 8a will be 2. Right, so therefore my partial fraction will be a, which is 2 over x minus 2, b, which is 3, and C would have to be 1. All it to be 1. So what we have learned into practice, let's see if you can do these questions. So to first of all, we have to check if the algebraic fraction given is a proper fraction. Right, do you remember how to check if a fraction is proper or improper? Yes, you check for the degree of the numerator and also the degree of the denominator. So what is a proper fraction? So a proper fraction is when the degree of the numerator is less than the degree of the denominator. That is step 1. So once you have checked that it is a proper fraction, the next step is to examine the denominator and to express it as partial fraction. So if you look at the denominator, it comprises of a linear factor. So for the linear factor, we can let it equals to a over x, 2x plus 1. And it also comprises of a repeated factor. So for that repeated factor, we can express it as b over x minus 2 plus c over bracket x minus 2 squared. Right, then the next step is to combine all of them into one single fractions. Okay, and I believe you should be able to do it. So try to do it on your own. If you don't get the answer for the first time, don't give up. Try again. Alright, so you should be able to continue it on your own. Recap of what we have learned so far. So we have learned how to express algebraic fractions with linear denominator. We have also learned how to express algebraic fractions with repeated, where the denominators are repeated factors. Right, what we're going to learn next is that what happens if the denominator given is an irreducible factor, irreducible quadratic factor, irreducible quadratic factor. So a quadratic factor must be highest power is 2. Right, so a quadratic factor is like a in the form ax squared plus bx plus c. Right. So what is an irreducible quadratic factor? A reducible quadratic factor would be, let's give an example, x squared minus 3x minus 4. This is a reducible one because you can actually factorize it into x minus 3, can factorize into x minus 4 and x plus 1. Another example is, let's say if you have x squared minus 25. This one can be factorized into x plus 5 and x minus 5. Okay, so the two examples I've given to you are reducible quadratic factor. So irreducible meaning you cannot be factorized it any further. Okay, you can't factorize it any further. So they are mainly in the form x squared plus a constant. So like x squared plus 4, x squared or 2x squared plus 3, or x squared plus 6, so on and so forth. So in the form ax squared plus b, where both a and b are constants. Right, so these are called irreducible quadratic factor. So the examples that I've given on the left hand side, alright. So if you are given two fractions, as usual, right, we will start off with two fractions because this is what you have learned already. The earlier knowledge you have learned is to learn how to combine two fractions into one fraction. So the examples on the left, you have a fractions with the linear factor, and then the second one, it's one with the quadratic, irreducible quadratic factor. Okay, so you combine them into one, and this is what you get. So now if we reverse the process, if you are given this, okay, given this huge algebraic fractions, how are you going to express it as two partial fractions? All right, so if you examine carefully on the left hand side, if it's a linear factor, it's always constant over linear factor, right? Because the second factor, the denominator, is a quadratic factor, right? It's x squared plus 6. So the numerator, you look at the numerator, here the numerator is 5x plus 3. So it's actually 1 degree less than your denominator. You see your irreducible quadratic factor here, it's of degree 2, and then your numerator is of degree 1. Okay, so how do you form a factor that is 1 degree less than x squared plus 6? You will be in the form bx plus c. Why do I use the letter b? Because the first partial fractions already used up the letter a, right? So subsequently, whatever letters I have to use, I can't be using a again because I already used it up. So I have to use b, bx plus c. Why bx? Because it has to be 1 degree less than the denominator. The denominator is of degree 2, x squared. So 1 degree less than your denominator will be a linear one. Okay, so the linear factor is bx plus c. Right, and then you do as per normal, combine these two partial fractions into one, and you apply the substitution method using different values of x to eliminate different constant. If you look at the first one, we let x to be -1 so that we can eliminate both your b and c, so that we can find the constant a. And then the second one, we let x equals to 0. Why is that so? Because so that we can eliminate constant b. Right, and then if you have found a, found b, you can use any other values of x except -1 and 0 to find your constant b. To repeat what we have just learned, if you have a proper fractions where the denominator is in the form x squared plus c squared, x squared plus c squared is an irreducible quadratic factor, right? Then the partial fractions that you will need to use will be in this format that I've circled it for you in green. Right, so let's look at one example. First of all, let's check to see if it's a proper fraction. Yes, the numerator is of degree 1. The denominator is of degree 3. Okay, do you know why it's of degree 3? Right, so let's examine your denominator. I have a linear factor. Okay, so this is my linear factor. So I can break it up into a over, express it into, the linear factor can be expressed as a over x plus 1. And then your irreducible factor, quadratic factor, we can express it as, after you've already used the letter a, then the next letter you have to use will be bx plus c. Okay, it will be a linear factor now, because now your denominator is a quadratic. Because your denominator is a quadratic, your numerator will have to be in the linear form. Alright, so the next step is that we'll combine them into one single fractions. Okay, and then we will compare our denominator with compare our numerator with the numerator of our algebraic fraction, which is 8x minus 27. Alright, so I'm going to use substitution. So I should, let's make this equals to 0. If you let x plus 1 equals to 0, so 0 times b x plus c, you would eliminate your b and c. So if you let x plus 1 equals to 0, then we're substituting for x equals to -1. Alright, so after finding a equals to -5, let's see which constant we can eliminate. We can actually let x equals to 0. Okay, if you let x equals to 0, you can eliminate your b, and then you can find your constant c. So after finding the value for your a, just substitute into your identity. And then we say that we want to let sub x equals to 0. So I have -5, 0 squared is 0, plus 6 plus 0 plus 1 is 1. b times 0 will be 0. So left only c. 8 times 0 will be 0. So 0 minus 27. So you simplify further, it will give you c equals to -27 plus 30. So c will give you 3. Okay, so after we have found the values of a and c, you can use any other values of x to find your constant b. But of course, you're not going to use x equals to -1 and x equals to 0 anymore. Think about why we don't use that anymore. Right, so I'm going to use, I'm going to let x equals to 1 to find the constant c. Alright, due to the lack of space, 8 times 1 is 8. 8 minus 27, that gives you -19. Alright, so we would end up getting 2 bracket b plus 3 equals to -19 plus 35. That will give you 16. And we need to divide both sides by 2. So b plus 3 will be 16 divided by 2 gives you 8. Therefore, your b will be 8 minus 3, 5. Alright, so after finding the values for all your constant, right, we can write down the answer. So therefore, the partial fractions are okay, a, which I found it to be -5, so it's -5 over x plus 1. B, we found it to be 5, so that will be 5x. C is 3, so plus 3 over x squared plus 6. So that will be our partial fractions. Put our knowledge into practice. Now, just a word of caution. If you look at x squared plus 4, please do not mistake it as x squared minus 4. X squared minus 4 can be factorized into x plus 2 and x minus 2. However, x squared plus 4 is irreducible. It's an irreducible quadratic factor. Okay, so when you examine the denominator, you have to look at it carefully, right? Look at it carefully. And then the next thing also, you need to check if it's a proper fraction. Right, after doing this one, you can just apply what we have learned. So to start you off, Right, the first factor is a linear factor, so we can express it as a constant a over x plus 2, and then your irreducible quadratic factor, okay, is x squared plus 4. So your numerator will be a linear factor in the form bx plus c. Okay, then you should be able to continue on your own. Right, so if you don't get the answer the first time, please don't give up. Try a few times and you should be able to do it. We should congratulate ourselves. Okay, we finally come to the last part of your partial fractions, and that is what happened if you're given an improper fraction. Right, if you're given improper fractions, can we still apply what we have learned so far? Right, the answer is yes, but before you apply what we have learned so far, okay, if you are given an improper fraction, you have to do something very, very important. All right, this something very, very important is that you have to use long division. Okay, you have to use long division to express your improper fraction, okay, in the form of quotient plus your remainder over your divisor. Right, and if you look at the screen there, okay, on the left hand side, if this is your improper fraction, if you've forgotten what the improper fraction is, right, let's do a recap. Improper fraction meaning the degree of your numerator must be more than or equal to the degree of your denominator. So in this case here, the degree of your numerator is 3. Your denominator degree is 2. Alright, so 3 obviously is more than 2, hence this is an improper fraction. Okay, so when you use long division, right, that will be your dividend, and then 2x squared plus x will be a divisor. You work it out, you will have your quotient, your 2x minus 1 is your quotient, and then you will have remainder 11x plus 4. Okay, so this one can be expressed as quotient, 2x minus 1 is your quotient, plus, okay, this is your remainder over this is your divisor. Right, so which is the one that you applied the concepts of partial fractions? You applied it on this part here. Okay, you leave your quotient untouched, and then you actually apply partial fractions to this portion here where I put the asterisk there. Okay, let's put what we have learned into practice. First thing first, let's examine if this is an improper fraction. Okay, this is an improper fraction. Why is that so? Right, if you look at the numerator, that is of degree 3, and if you look at the denominator, that is of degree 2. So the degree of the numerator is more than the degree of the denominator, hence this is an improper fraction. So for improper fraction, we have to apply long division to decompose it. Okay, so I'm going to use long division now. Okay, so the first term will be 4x cubed divided by 4x squared. That gives you x. And then your x will multiply with each individual terms of your divisor. So that will give me 4x cubed plus 4x squared plus x. Give me 8x squared plus 12x. Alright, so the next step is 8x squared divided by 4x squared gives you 2. So 8x squared plus 8x plus 2. And that will give us 4x minus 2. Alright, so not to forget also, we still have a positive 7 here. So it will be 4x squared minus 2 plus 7. That gives us 4x plus 5. Okay, so the 4x plus 5 will be my remainder. This is my remainder. Right, so our algebraic fractions can be written as equals to the quotient, x plus 2 is our quotient, plus our remainder is 4x plus 5, over our divisor, which is 4x squared plus 4x plus 1. Right, so alright, so we will leave the quotient alone. So which is the one that we have to apply the partial fraction? This will be the one that I've just boxed it up for you. Okay, so how do you express it? How do I express it as a partial fraction? First of all, let's look at your denominator. Alright, so if you look at the denominator, we can actually factorize it further. This is actually a quadratic denominator. Right, we can factorize it into 2x plus 1. Another 2x plus 1. Okay, right, so your 2x plus 1 with another 2x plus 1, what does it remind you of? It's actually a repeated linear factor. Alright, so how do we express algebraic fractions with a repeated linear factor? Do you remember? We can let it equals to a over 2x plus 1, then plus b over bracket 2x plus 1 squared. Okay? Right, and then we combine them into one single fraction. Alright, and then we let it equals to our numerator, which is 4x plus 5. Okay, and we use substitution method. Here I'm going to let x equals to negative half so I can eliminate my a. So my a will be gone. So b will be 3. Okay. Right, so I'm going to continue here. Right, so after finding the values of b, I still left with a. So I can just substitute x to be any other value except negative half. So I'm going to let x equals to 0, which is usually the best one is x equals to 0. Why is that so? Can you think of a reason? So if my x is 0, I will have a times 1 because 2 times 0 is 0. 0 plus 1 give me 1. I've already found b to be 3, so I can substitute inside there. And then 4 times 0 will be 0 plus 5 give me 5. So my a will be equals to 5 minus 3, 2. Alright, so I found the both constants. So how do I express my answer? So my answers will be, okay, serious apology. I will have to write it here due to the lack of space. So therefore, the partial fractions will be okay. The quotient, don't forget the quotient, x plus 2. All right. And then your two partial fractions, a over 2x plus 1. The values of a we found to be 2. So it's 2 over 2x plus 1. Followed by b, which is 3 over bracket 2x plus 1 squared. Okay, so this is how you actually manage an improper algebraic fraction. All right, it's very long, but it's don't give up. Okay, don't give up. You just need to practice a little bit more and you should be able to get a hang of it. All right, so let's try to do this on your own. So if you don't get the answer in the first for the first try, please don't give up.